Alright, so what we're going to do today is we're going to continue. This is Math 331, Lecture 17. The goal today is to continue with attacking various problems. We had a couple of things related to hats and whatnot. I want to first do a checkerboard problem. And so when you consider an n by n board, and you have 1 by 2 tiles, can you cover? So you can't put down a tile on top of another tile. So what do you think? When do you think you will be able to cover an n by n board with 1 by 2 tiles? Yeah.
N is even.
Yeah, if n is even, you can cover it. It's not a problem. Just go in rows of 2. Okay, so let's make the problem a little bit more interesting. What we do now is we take our board. 1, 2, 3, 4, 5. 1, 2, 3, 4. I can't do. So I don't want to do 5. So here is now a 6 by 6 board, and I will remove the bottom left corner and the bottom right corner. So when we had the full checkerboard, you said it was doable. It wasn't that hard to give an explicit construction. So now, can you still cover? There's going to be an even number of squares. So there's at least a chance, right? Because every time we put down a tile, we put down an even number of squares getting covered. So there are several ways to resolve this problem. One is if you can explicitly give me a covering, then that proves you can do it. Or you can show that a covering exists without explicitly giving it. This is the non-constructive proof. Or you can show that no such covers exist. So what should be your first step in analyzing a problem like this? What should we do first? Smaller cases, excellent. So let's do the 2 by 2 case. So here's our 2 by 2 case. Hello. So we're trying to cover checkerboards n by n. We know n has to be even, and we're removing the bottom left and the bottom right corner to see is it still doable. And so we've had a great suggestion of looking at smaller cases. We can't do a 2 by 2 board. So the answer is no. Although maybe the 2 by 2 case is so small that it's not good enough to really see what's going on here, that we haven't really settled into the limiting behavior. So let's look at the 4 by 4 case. So for the 4 by 4 case, so I think this is the 4 by 4 case. We can start going through all the different possibilities to see can we cover. Right? There's at least more things to check now. So where do you think might be a good place to start for our first piece? Yes?
One of the 2 corners that has the corner removed.
That has the corner removed?
No.
Okay, that has the corner. Okay,
yeah.
So we can either go up or we can go this way.
It doesn't matter.
All right, so let's say we go this way. So that now gives us this piece here. Now we know this piece has to be vertical like this. Now we could have 2 vertical here or 2 horizontal here. It doesn't really matter. Either way, we're going to get those 2 pieces. So we know these 2 will have to be covered. Now over here, that tells us we're going to have to go this way. So it has to be like this. Well, now to get this piece, we have to go like this. And so we see that we can't do it like this. Now we need to just look at it that way. That way also doesn't work. So I'm not going to do that. I'll leave that as an exercise. We'll see the answer is no as well. It's, oh yeah, so going here would be the same as going here by. Oh good, excellent. Excellent. We can flip it about that line. Good, we don't even have to do that as a separate case. Outstanding. So the answer is no for the 4x4, but maybe the 4x4 is not large enough to truly see the limiting behavior. So let's look at the 6x6. Write a computer program. After some computations, it returns no. 2018 by 2018, our computer program has been chugging for quite a while and returns us an incredible string of no's. So at this point, I believe I'm finally beyond the case of small n, that this should hopefully be enough to see limiting behavior. There's a paper I wrote with Professor Goldmacher and some students where we are calculating moments of some distribution. And it turns out the first 7 moments agree with the semicircle distribution, but the 8th moment differs. And so there were combinatorial reasons why, if you look at 7 or smaller, you haven't gone far enough to see the limiting behavior. Sometimes it does take a while. Once you get up to 2018 by 2018, it's pretty clear that, okay, this should be a no. Yeah, I don't see anything that's going to somehow emerge when we go further. The 2x2 case could just be 2 degenerate, these are isolated blocks of size 1 by 1. Any thoughts as to how you can prove that you can't do it? Yeah.
Maybe you could do something like starting with like an end condition and working backwards or something like that.
But what would be the end condition?
Something like, I guess, like covering maybe like one of the last squares, or I don't know, maybe you'd start from the beginning and covering one of the first squares. Like it seems like the way that you did it up there, it was sort of like you chose a move and then you kind of had to do the different ones.
Yes. So that was a brute force attack.
Yeah.
And the problem is, we were fortunate, I missed it, but was mentioned that by symmetry, there's really only one way to try the 4x4 case. As it gets larger and larger and larger, you start to have more and more freedom in how to put things down. And so you can brute force any one of these, but to then get the general case, it's not going to work. So we want to think about how we're putting the pieces down, and the question is, what technique have we been studying recently?
Pigeonhole.
We've been studying pigeonhole, but before monovariant. So the monovariant is an art form. So what you want to do is you want to imagine your board, and the board's going to look something like this. And you want to associate every time you put down a piece to some quantity. So we'll let A0 be the value when no pieces are put down. A1, the value when one piece is down, all the way down to the last piece we put down. And we need to associate a quantity. Any thoughts on what we could associate?
I feel like I've heard this problem before.
You have. This is a famous problem. And this is one of those problems where if you look at it the right way, you're like, oh, damn, that's what I need to do.
Well, yes, I think I know it, but I feel like it like ruins it for everyone else.
Okay, so but did you remember what you're supposed to do?
I think so.
Okay. All right, so hold off. Does anybody have any thoughts on what we could associate? And again, this is the whole point of this class. This is why I'm happy. This is, I think, the only time in your college career where we can afford to spend this much time thinking about a problem and talking about the thought process. Is how do you come up? And if you have no idea, start asking yourself, when I think of a checkerboard, what do I think of? What does the checkerboard look like? What does it have? It has black squares and white squares. How many black squares does the n by n checkerboard have when you remove the two corners?
Well, either too few or too greater than.
Right, so how many black squares do you start off with?
N squared over 2.
So there's n squared squares divided by 2. So you start off with n squared over 2 minus 1. And we know n is even, right? Otherwise there's no chance. So we could say maybe it's 2k squared over 2 minus 1 is 2k squared minus 1, n equals 2. And similarly, we have 2k squared over 2 minus 1 is 2k squared minus 1. Is this right?
Wait, aren't you subtracting 2 from 1 of them?
Yes. So I don't subtract off 1 from each. One of them loses 2 and one of them loses. Without loss of generality, do you want to assume the black is losing 2 or the white?
Let's just do black.
Alright, so black loses 2, white loses none. So they're both even numbers. What happens every time you put down a tile?
You remove 1 in black and 1 white.
You remove 1 black and you remove 1 white. So if the monovariant is the number of black squares covered or the number of white squares covered, it always goes down by 2. So so you could have as a monovariant the number of white squares, and then you'll see that if you place everything, there'll be 2 white squares left. And that's impossible. When you get to the last tile would have to get 2 white squares. Another thing you could do is it could be the number of white mod 2. And now it's no longer a monovariant, it's now an invariant. If you just look at the parity of the number of, oh no, it would flip, never mind, we don't want to do mod 2. Better just do number of white, sorry. Just do number of white. And so when you do this at the end of the day, when you're trying to place your last tile, you'd have to put down and cover 2 whites. Can't be done. So this is the monovariant. Was this what you were thinking of? The hard part is coming up with what is the right object to study. That is the challenge. And so sometimes it helps to do special cases, build intuition. Sometimes it helps to just ask, well, what do I know about a checkerboard? When I think about the checkerboard, what does it look like? And does that matter? Then, of course, you could generalize. What if I gave you a 1 by 3 tile? Should there be an analog? What if I removed 2 corners that were the same color? Do you think it's doable now? I mean, given that things would have to be even, I would just put even ones here, and then just fill it in with rows. So if you remove 2 on the top or 2 on the bottom or 2 on the side, it's actually going to work out without any trouble. Okay, so I just wanted to do one more monovariant. And then let's go back to some of the riddles we were talking about. So do people want to do the general code first, or do you want to do the hat problem? Hat problem. All right. So we have, there's a tremendous wealth of hat problems. I think this was the hairstyles. All right. So each person can see the other 2. They can't see their own hat. And it's weird on the blackboard. The colored in one is the white hat, and the non-colored in one is the black hat. And each person has a 50-50 chance of getting either hat. So we all agree that, and the rule is, you wait 5 seconds, say white, black, or be silent. If anyone is wrong, you lose. All speak right. You win. All right. So do we agree that you should not be able to have anybody correct more than half the time? Because you can't see your own hat color. You haven't proven this rigorously, but does it seem plausible that no one should be able to speak correctly more than half the time? Because whatever your strategy is, it's based on what you see. It has nothing to do with what hat I put on you. So I can change your hat color. So it doesn't seem like there's any way you can speak and, over time, be correct more than 50%. All right.
how I would do it is say you only speak if both the other two people of the same color hat. What the people you see. And then there's a 75% chance that you have the other color.
Oh, excellent. So you only speak if you see two hats that are the same color, and then you speak and you say you have the opposite color hat. So let's go through and just analyze this by brute force. So players 1, 2, and 3. So these are the colors, and this will be right or wrong for 1, 2, and 3. So in problems like this, you always want to make sure you just go through and list the cases very mechanically, very methodically, so you don't make any mistakes. So I'll go white, 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 black, 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 black. Then I'll go white, white, black, black, white, white, black, black, white, black, white, black, white, black, white, black. There's many ways you could have done it. This is just one way that's guaranteed that I won't miss any cases. So in this one, you only speak if you see two hats that are the same color and you say the opposite. So what happens here? They're all wrong. So it's wrong, wrong, and wrong. And the result, death. This is the Lord Vader not so forgiving school. What about the next case? Who's the only one who speaks? 3. And 3 is correct, so you win. What about this case? 2. It's always a minority. Win. And then in this case, the first one, win. In this one, first one, win. In this one, the second one, and you win. 1, 2, 3, 4, 5. So 6, 1.
And then the last one.
Did I miss one? Oh no! 1, 2, 3, 4, 5, 6. Okay, good. 7. So this one is the last one, and you win. And the last one is wrong, 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 and death. Okay. So this strategy will survive, will win 75% of the time. And if we look on each person is right twice, wrong twice, and silent 4 times. So everyone speaks 4 times. They're right 50% and silent the rest of the time. So what's going on? Why does this work so well?
So this is not rigorous, but it seems like you're concentrating like all your wrongness in like 2
Yes.
possibilities.
When I'm wrong, boy, am I wrong. And when I'm right, I just barely squeak by. This is not a bad idea. If you only have finitely many resources, you want to put your chips in the place where they will have the greatest effect. We have elections coming up right now. When you're having elections for a congressman or senator, does it matter by how much you win? You might be able to argue I have a mandate or not, but at the end of the day, if you win, you go to DC. If you lose, that's it. So when political parties are designing their districts, I'm sorry, I shouldn't say political parties are designing their districts. Congressional districts are chosen, of course, in fair ways. Right? What's the phrase I'm thinking of? Gerrymandering. Who knows where gerrymandering, that phrase comes from? Massachusetts. Who?
Cherry.
Yeah. I mean, it's not a bad. Is Jerry his first name or last name? Last name. Eldridge Gerry used to be governor of Massachusetts, was involved in the Revolutionary War. You talk about gerrymandering districts. You have some districts that have extremely strange shapes, where they'll snake around a highway and go something like this. Or frequently what you'll do is you'll have a big city, and you'll have your district over here with the suburbs, and it will snake in and take a chunk of the city. And they do this to try to get districts where your party can just barely win. And so if you have a certain number of voters, you want to spread out your voters to maximize how many districts you can win. If you look at it this way, I do not want to get into politics here, we're going to have the checks versus the X's. Okay? And each side has 6 voters that they can choose where they want to live among the 8 districts. And Czech has adopted the strategy of completely capturing 2 districts. I'm sorry, Cross X has adopted the strategy of completely capturing 2 districts. Czech has taken the different strategy of just putting 1 person in each of these. There was talk, I believe, years ago of the Libertarian Party basically trying to encourage all their people to migrate to a small state and just take over the state government. Go for a state with a small population where you can do something like this. There is no way Cross is going to lose districts 1 or 8. They have every seat. They have every vote. But they end up only with 1/4 of the districts. Whereas Czech strategy netted them 6 out of 8. So the mathematics behind this is actually extremely valuable. When people are designing congressional districts, there is now a lot of court cases and a lot of mathematics behind what is a fair district. There's a lot of really good math papers on what would be a good measurement where you can say, nah, this is not designed reasonably. I always like the kindergarten test. It must be a shape that a kindergartner can recognize. There's a lot of shapes that are really bad. Some people like to look at ratio of perimeter to area. There's a lot of things you can use to study things like this. There's other applications of this. Anybody ever see the movie Minority Report? The short story was better than the movie. Do you know who the author was for cultural extra credit? Philip K. Dick. He was also the author of Second Variety, which I think is related to the Terminator movies. He was also the author of Do Androids Dream of Electric Sheep, which is Blade Runner. Also, The Man in the High Castle, which is now, I believe, a series on Amazon Prime. Very famous science fiction writer. The military often does the following strategy. Let's say you want to bomb somebody, and you're going to try to calculate where to shoot things. You have 3 computers calculate it, and it's majority rules. If 2 out of 3 of the targeting computers give you the same solution, that's where you bomb. And the odds of 2 of them getting the same wrong answer is so small that you can be reasonably confident if 2 out of 3 tell you something, then you know that's the error. So I mentioned earlier that this is the basis of a lot of modern e-commerce. Is there anybody here who has not watched streaming video, downloaded a file from the internet? I think I can safely assume in the 21st century, everybody has done something like this. You're getting a bunch of bits, a bunch of zeros and ones, and you want to know, have you received the information correctly? So you get packets that are being sent to you all the time. So instead of transmitting messages, we can just transmit zeros and ones, and I can have maybe 0000 means A, 0001 means B, etc., etc. You can come up with various code words. How do you know if you got the message correctly? How do you know that there wasn't a transmission error?
You give a checksum.
So one possibility is a checksum. Is, let's say you have a bunch of zeros and ones, then you have an extra digit at the end, the checksum digit, which will be 1 if the sum is odd and 0 if it's even. So I think they often do this with like book codes. So maybe I have 101101101101, and then the checksum is 0. So it's 0 if the sum here is even, 1 if the sum is odd. So 1, 2, 3, 4, 5, 6. It's an even number, thank God, and I got a 0 here. What if I give you 1, 1, 0, 0, 1 0 1 1 1 1. What do you know now? So it's wrong. Do you know where the error is? No. And in fact, where could the error be? I'm sorry?
Anywhere in the
Anywhere, including
check.
the checksum, right? The error might be, this could have actually been the correct message. The error might actually be in the checksum. All this does is tells you a mistake was made. So a lot of the theory about some of this was developed by Richard Hemming when he worked at Bell Labs. He was low person on the totem pole, and he could essentially get his programs to run, on the weekends. And this is back in the days of punch cards. You would write your program on punch cards, they'd run in the machine, and then you would come in on Monday morning and they would say, it crashed on line 15. And so then he fixes it, and the next weekend, okay, it crashed on line 43. And eventually he exclaims in frustration, if the machine can detect that there's a mistake, why can't it fix the mistake? There's some problem with the audio. So you can detect an error was made. Why can't you fix it? So over here, you can detect that an error was made, but you don't know where the error is. So the checksum is extremely valuable. It allows you to know an error was made. If it's easy to retransmit, then the checksum is terrific. It's one of my favorite inventions in the 20th century. It essentially uses checksum technology. You see this every time you buy something at the supermarket. Where do you see something like the checksum at the supermarket?
Barcode?
Yeah, the barcodes. When you scan the item, it's incredible. It updates the inventory of the store immediately. It also correlates your purchases so that they can see what you like to buy. To me, it's one of the greatest inventions of the 20th century. You no longer have people going through, you can update in real time what people are buying. It's a phenomenal invention. As an aside, you know the Target pregnancy story? Okay, so anybody else know this one? All right, so if I get it slightly wrong, please correct me. A father gets a set of coupons from Target for various products, basically products related to pregnancy items. And he's furious and he yells at the manager of the local Target. He says, look, my wife and I are well past the age of having kids. And, my kids are too young to be having kids. What are you doing giving me coupons like this? And the manager's very apologetic. We're very sorry. And then a few days later, the manager contacts the father again to just make sure everything is okay and apologize once again. And the father is extremely sheepish. And it turns out his high school daughter was engaged in extracurricular activities that he was not aware of, and those coupons will be valuable in the foreseeable future. Target knew he was going to be a grandfather before he did. And the reason is they were able to look at the correlations between purchases being made by his daughter. And these purchases correlate well with being pregnant. And if you're pregnant, you would probably want coupons like this. And we want you to do one-stop shopping. We want you to come and spend your money at our store. Now, it's kind of hard for people to complain about being targeted when they go to a store that is actually named Target. But people don't like to feel like they are not special. And so it was bad publicity for something like this. But Target still wants to get their business. If you have kids, and if you don't know what it's like, if you want to borrow Cam and Kayla for a weekend, just let me know they're yours. It's hard sometimes to travel to multiple stores, especially when the kids are very young. You want to get all your shopping done at once. So you want to give people coupons to draw them to your store. But if people feel like they're being targeted, they will be unhappy. So do you know what Target did?
Just give you some wrong ones.
Yes, in fact, deliberately wrong ones. Things that would be like the exact opposite of what you would want. To make it look like you just have a selection of random coupons with a couple of key coupons that they know you want. A brilliant strategy. So if you're in a supermarket, the checksum is really easy to do. If all of a sudden it doesn't scan your Life cereal, What do? Scan it again. It's not that hard to scan it again. It's very easy, and you can tell immediately if it didn't scan or not. So the checksum works very easily there. If you are sending transmissions to agents in the field, it may not be easy to transmit again. You may have a submarine that surfaces very briefly at a key moment in time, gets the message, and then dives under. So there's a huge trade-off here. The checksum lets you know an error happens, but it doesn't let you fix it. The minority report, majority report, can be used to fix things. So this is the TellMeThreeTimes method. So you send either 111 or 000. And that's the only messages you'll send. So if you send 111, that's basically sending a 1. And if you send 000, you're sending a 0. Imagine you now receive 010. You know a mistake was made. Correct? There's no way this can be right. What could the message be? Probably 3 zeros. But what could the message be? What is the set of possible messages? Yeah, it's these two things. This is what it could be. Now, what do you think it's likely to be?
Probably the zeros.
Yes. And as long as the probability of a transmission error is less than 50%, this is more likely. What if your probability of a transmission error was greater than 50%? What if you had like an 85 or even a 95% chance of a transmission error? Yeah, just switch it. If you're in a system that is so bad that 99% of the time you're wrong, then just deliberately send the wrong thing. Right? So if you're really, really wrong and you know that, it's as good as being really, really right. I will risk another cultural attempt. Seinfeld, please. Has anybody ever watched Seinfeld? Okay. Do you know the episode The Opposite with George Costanza?
Probably not. It's been a while.
All right. So George is remarking to his friend Jerry that every decision he's made in his life is wrong. Every time he's had a choice to make, he's always made the wrong choice. So Jerry tells him from this point onward, you should do the opposite of what your instincts are. So later in the episode, there's an attractive woman at the restaurant counter who's looking at him. And, I can't talk to her. And then they say, you should do the opposite. So he goes up to her and says, my name is George, I'm 35 years old, I'm bald, and I'm unemployed, and I live with my parents. Hi, I'm Victoria. And so he ends up going on a date with her. She ends up having an uncle who works for the New York Yankees, and he meets the owner of the Yankees. And the owner of the Yankees says, it's nice to meet you. And he responds, I wish I could say the same to you. I don't know how much longer we citizens of New York can sit by and watch what you do to our beloved New York Yankees. And he just unloads on Steinberg, and Steinberg goes, hire this man. Because if you are essentially always wrong, and it's a binary choice, that's the important part. That's extremely important. Okay? If it's a binary choice and you're always wrong, then you are essentially always right. You just do the opposite. So in a situation like this, if we have an extremely high probability of making a mistake, that's essentially as good as being almost always right. And so this allows us to correct this to 0, 0, 0. It doesn't mean that 0, 0, 0 is the correct item. But if the probability of an error is small, the probability of 1 digit flipping is much smaller than 2 digits flipping. It's actually possible if we get 0, 0, 0 that we meant to send 1, 1, 1. And all 3 digits were flipped. So what could you do to have even more security?
Increase the size.
You increase the size. So why the hell don't we do that? Why don't we send the same number 5 times or 8 times?
Increases the amount of space that it takes to send a
Yeah, it increases the time it takes to transmit the message. What fraction of your message is actually information when you send 111 or 000? 1/3. So more than half of your message is actually redundant checks. But it allows you to fix the mistake. This solves Hamming's problem of why the hell can't the computer fix the mistake? It knows there's a mistake. But it's expensive. You are now in a situation where more than half of your message. The checksum just alerts you very quickly. And as long as you have your product items sufficiently spread out, this is usually fine. So if people are interested in stuff like this, we can talk more. Healing did not stop here. He actually created a way to send messages where a majority of the message was information and a minority of the message was checking to make sure things were correct. So if people are interested, let me know, or just nod your head vigorously right now. I'm seeing people nodding. So we'll do that on, this is Friday? So we'll do that on Monday. We will talk about how the hell, you can think about this over the weekend, can you actually get above 50% useful? And then how far can you push this? Can you get 80% of the message useful? Can you detect multiple errors? So there is a whole science about this. And when you think about how many things we are transmitting, this is phenomenal to be able to do stuff like this. And it's essentially the same thing as what we're doing over here. If you look at this, if we know that there are two things that are the same and one thing that's different, this is essentially flagging which thing to change. Is we're basically saying we should really only be sending these two messages. And anything else is a mistransmission. And it's telling us how to fix things. So this is not just a cookbook problem. This is a problem that has real meat. And then this is related to the hot hand, which I promised I would talk about. So there is argument as to whether or not certain basketball players are just hot at times, and they're just making shots, or certain baseball players are just hot and getting hits certain amounts of time. As a Red Sox fan, I am grateful that Price finally had a really good game in the playoffs and pitched beautifully and got his first playoff win. If you have enough events going on, unlikely things will happen. You should be shocked if unlikely things don't happen. If something happens 1 in 100 times, and you look at 3 occurrences, do you expect anything to have happened? Do you expect the unlikely event if it happens 1% of the time and you have 3 samples? What if you have 100 samples? Yeah, you expect it to have happened once. What if you have 1,000 samples? You expect it to happen 10 times. So even though the event is unlikely, if you do it enough times, you will see that it happens. How many of you have ever heard news reports where they talk about an unlikely event? Yeah. We can't believe that this coincidence happened. How many times do you hear news reports and nothing was out of the ordinary today? Everything happened the way we expected. That doesn't make the news. It's when you get like a strange lottery number, I think like 911 was like the lottery number in New York City a year after 911, something like that. I know years ago, Clinton and Obama in 2008 had exactly the same number of votes in Syracuse, New York, which a lot of people said was extremely unlikely. If you say beforehand that it will be Syracuse where they have the same number of votes, that's unlikely. If you look at all the places that are voting, they should be tied somewhere, that's extremely likely. And so one of the things I want you to get out of this is, what's the right way to look at things? You do expect unlikely events to happen. Okay, so we've talked about this. We've talked about this to use for error correcting codes. For the hot hand, it's very similar. So what they look at is, if you've made your previous shot, what's the probability you make your next shot? Or you could look at it as, if you're tossing a coin and you get a head, what's the probability the next coin is a head? And I think I sent you guys the paper. And so the paper looks at, I think, tossing 3 coins. And it's, if you have a head, what's the probability that the next toss is a head? And it's very similar to something like this. This is essentially the idea behind what's going on and why it looks like a paradox, but it's not. And what's really happening is, it's how things are spread out. So if you look at the paper, do you remember which way it goes? Do they find that you're slightly less likely or slightly more likely? I can't remember.
I think it's less.
I think it was less likely. So you're slightly less likely to get ahead if you had previously gotten ahead. But if you look at it, on average, it's got to be 50% of the time you get ahead after ahead. But they were looking at it by breaking it up into these bins. And so if I look at it this way, each person is right half the time and wrong half the time. But if I look at it this way, I can get a different feel. And so much of life is how you choose to form things. You can try to mislead people. Rather than doing the code cryptography problem, we'll save that for next time. I will do one of my favorite ways to mislead people. So, let's see, 3 of last 4 games. So let's say I tell you your team has won 3 of their last 4 games. What winning percentage is that? 75%. Is that a good winning percentage? If you think of any professional sport, 75% is almost always good enough to make it into the playoffs. Baseball, basketball, hockey, clearly 75%. Football is more extreme. We will actually get teams close to 100%, but most of the time 75% is enough to... I don't know any football team that's missed at 75%. Do you think the team is playing well? They've won 3 of their last 4 games.
Hard to know.
They've won. What do you mean hard to? I just told you they've won 3 of their last 4 games.
Playing.
Okay.
Well, I mean,
Miss Smith's school for the Williamstown Elementary School 3rd graders, and so let's say they're playing reasonable teams.
so you can like write out every sequence of like 4 games.
Good. But let's think a little bit. So this is their last game 2 games ago, 3 games ago, 4 games ago, 5 games ago, and so on. What happened 5 games ago?
They lost.
They lost. You go. You know. We do know they lost 5 games ago. Why do we know they lost 5 games ago?
Say 4.
Otherwise, I'd say 4 to 5. So we know there's a loss. What happened 4 games ago? They won. Could they have lost 4 games ago? What would I have said? They've won 3 in a row. So you know it has to look like this. So we know that in here they have 2 wins, 1 loss. So in their last 3 games, they're at 66%. In their last 5 games, they're at 60%. In both situations, they're essentially winning 1 game more than average. It's not that impressive. I have jiggled things deliberately to make things look better than they are. And so what I like about this problem is the ease in which you can mislead people by how you phrase things. And so what I want to do now...
Sorry, where's the 66% come from?
Well, so we know in their last 3 games they have 2 wins and a loss.
Oh, okay.
So because they have 2 wins and a loss, in their last 3 games they're playing 66. In their last 5 games they're playing 60%. I am deliberately cherry picking how to change things. So let's look at f of n is n squared plus n plus 41. What's f of 0?
41.
What do you notice about 41? Prime.
Isn't this like part of protocol?
What's f of 1?
43.
What do you notice about that? What's f of 2?
47. 5.
And then if you go all the way up to f of 37, log, it's prime. What do you think?
F of 41.
So you know to jump a little bit ahead. So I deliberately stopped at 37. It actually works all the way up to 39. It works for f of 38, and it works for f of 39 as well. And once you get to f of 40, it's no longer prime. Sometimes, if you have some freedom, stop your pattern a little bit early. So if somebody decides to investigate a little bit further, you've got something in the bank. For the stuff there, I couldn't do that. But there is a real art to how you can present information. So there's the phrase, there's lies, there's damned lies, Anybody know the ending?
Statistics.
And then there's statistics. If you color things just the right way, you're not lying. But you can definitely mislead people, and you can shape people into looking at things in different ways. How many of you have ever taken an exam with a red herring? A red herring is information that is entirely irrelevant to the problem under discussion. So a lot of times professors love to put stuff like this on, and then you've got to realize, no, this doesn't matter. So here, I just wanted to end with the power of being able to manipulate perceptions. Just how careful you have to be when people say, isn't this surprising that this has happened? Well, what are you choosing to relate to me? Are you choosing beforehand, this is the story I'm going to cover? Or are you then waiting to see what happens, and then that's the story you elect to cover? So when things look surprising, this goes back to the hot hand. This goes back to, is somebody a clutch hitter? Who are they choosing to talk about? Are they talking about, I'm going to specify this guy before the season begins, this is a clutch hitter, this is a hot hand? Or do you wait and see lots of things that have happened, and then you cherry pick which person you focus on? All right, so for Monday's class, we will do the general code, and then we will lead into generalizations of what Hamming did with the Tell Me 3 Times, and see how you can use this to transmit a majority of your message as information.